Good evening. Welcome back to my channel once again. Previously, we have looked at how to determine the ground state term for p orbitals and d orbitals. Today, I want us to begin a new topic called crystal field theory, or under coordination chemistry. We are still looking at topics under coordination chemistry. So this is a crystal field theory. According to crystal field theory, when a ligand and a metal comes closer together, there is an interaction, but it assumes that the ligand is a negatively charged species and the metal is a positively charged species. So a negative charge and a positive charge coming close together. Then it also assumes that the d orbitals, they are degenerate and they have the same energy. Degenerate means that they all have the same energy, meaning that when the ligand has not approached the metal d orbitals all have the same energy, like this. Assuming if we take this the d orbitals 1, 2, 3, 4, 5, and this is the ligand. So in the absence of the ligand coming close to the d orbitals, all the d orbitals have the same energy. They all have the same energy. And then as soon as the ligand approaches the d orbitals, it comes in a certain direction. And therefore forms a bond, sigma bond, with the d orbitals of the metal. Therefore, the d orbitals of the metal, which have the same symmetry as the ligand, they form a stronger interaction, a greater interaction with the ligand. So the ligand is coming in a particular symmetry or in a particular direction. So d orbitals having the same geometry or the same symmetry or lying in the same direction as the ligand, they have a greater interaction with the ligand. So because of the greater interaction, their energy increases, or their energy are raised. The energy is raised. Just like if two people collide, then realize that there is heat generates among the two people when they collide. So in the same way, if the ligand approaches the metal, the d orbitals of the metal having the same geometry as that of the ligand, they have greater interaction with the ligand and they have higher energy. Then the d orbitals, which have a different symmetry or the different geometry as the ligand, they have less interaction with the ligand. Because they have less interaction, their energies are lowered, or their energies are decreased. Since some of the d orbitals of the metal have energy, since some of the d orbitals of the metal have symmetry or geometry which is the same as the incoming ligand, those d orbitals have higher interaction. Therefore, their energy becomes very high. In that case, the energy of those orbitals becomes different from the remaining orbitals. So since the energy is high, they move upwards. So there is a breakup in the d orbitals because of the different energies. So we call this breakup of the d orbitals of the metal the crystal field splitting. Now let's look at the shape of the d orbitals. We have 5 d orbitals. We have the dxy. The dxy lies in between the x and the y axis. Then the xz, the loops lie in between the x and the z axis. And the yz loops also lie in between the y and the z axis. And the x square, y square loops lie on the, take note of this, on the x and y axis. These are in between. This lies on the x and y axis. Then the dz square loops also lie on the z axis. So meaning that the dxy, xz, and yz all lie in between the axis. They all lie in between the axis. So if the ligand is coming in that particular geometry, then they will have a higher interaction with the ligand. But if the ligand is coming on the x, y, and z axis, then it means that the x square and y square and the z square will have a greater interaction with the ligand. But if the ligand is coming in between the axis, then these will have higher interaction with the ligand. So let's look at the shape of the orbitals. So we have the xy here, yz and xz. They all lie in between the axis. So as you can see from here, the loop, this is the loop of the xy. They are in between. This is the x-axis and the y-axis. The loops are in between. They are in between the axis. This is also in between here. They are in between the axis. This is also in between the axis. But when we consider the x square, y square, as we can see, this is the x-axis, this is the y-axis. This loop is lying on the x-axis. As you can see, it is lying on the axis. This is also lying on the y-axis. When we consider the z square, this is also lying on the z-axis. Lying on the z-axis. And this is the donut-shaped ring around the z-axis. Around the dz square orbital. Also lying on the x-axis. So these two orbitals have their loops lying on the x, y, z axis. And these three orbitals have their loops lying in between the axes. Okay. Thank you very much. Let's end here. This is a brief introduction on crystal field theory. Next time we'll look at how the interaction occurs in an octahedral complex and then tetrahedral complex. Thank you.